Our next concept is impulse. Impulse is simply when a force is applied for a time. You'll see what I mean by that. For a time, usually just a specific period of time, to change momentum. Change, I'll just put P. All right? So to see it, we can go back to Newton's second law, the real Newton's second law. F equals dP dt. And then we could apply the fundamental theorem of calculus, or we could bring the dt over here and integrate both sides. Whatever you want to do, you know that this is really P2 minus P1. If we look at the momentum change from 2 times that we call dt, it looks like that, and therefore you'd have F times dt, so if you integrated that side, it would look like the integral of F dt from T1 to T2. So to find the change in momentum from time 1 to time 2 is the integral of F times dt, right? So what we could also call this is just delta P, right? So the impulse, I, is equal to delta P, and it's equal to the integral from T1 to T2 F dt. So this is the impulse, and it is the change in momentum. That's all it is. It is literally delta P. It has units of kilograms meter per second. It is a vector. Okay, so it's just a fancy way of saying the change in momentum. You might see it written without the integral, so you need the integral if, in this case, of course, if the force varies with time. If the force varies with time, and if you're good at your calculus, you know what this looks like. If the force does not vary in time, then it's just F times delta T. So you could also say delta P equals F times delta T for if you have a constant force applied for some time. Let's think about reality, though. So what if I take this ball, right, and I drop the ball and it bounces back up, or I throw it down and it bounces back up? As it falls, it clearly has momentum down. MV is pointing down, the p vector is down, and it's getting bigger because the gravitational force is increasing the p vector. And then it hits the surface, and suddenly it has momentum up. It's because it received a brief impulsive force from the table, right? The table pushed it up. So let's see, what do we think that really looks like? So impulsive forces are usually complicated. If you think about it, the rubbery ball is going to act like a spring. So if we were to plot the real force versus time, force versus t, it would kind of be nothing, that it starts to touch, and you get a big force, and then the force goes away as it pulls away. Something like that. And the impulse would be the area under that curve, area under the FT curve. But often when we do problems with impulse, when we talk about impulse, we often define just the average force, right? So we could do it this way, or we could say, well, it was kind of like this, right, where this is F average. And you pick that average so that the area under this curve, F average times delta T, is the same as the area under the true impulsive curve. So in problems, you'll often see a problem written to say it felt a force of an average force of 20 newtons for 5 milliseconds. And then, if the impulse, you just multiply 20 newtons times 5 milliseconds. And you don't worry about what the force really looked like in real time. Also in these kinds of problems, one thing to watch for is to keep in mind the vector nature of the momentum and the impulse and everything. So for instance, if you were trying to calculate the impulse of the bouncing ball, right, the impulse that caused the ball to bounce, you would have here, if we call this the positive z direction, and it's falling at v initial, then at first your momentum vector is down, right? So p initial is minus m, I'll write the magnitude, the speed, right, I hat, or ij k hat, right? It's down. And then it says it bounces back up at v final. So keep in mind it's going the opposite direction. So p final is, in this case, positive, because it's going up. M, the speed final in the k hat. So keep in mind that the delta p that's equal to your I, it's p final minus p initial, but vectors. All right, so final mv final, I hat minus, and then minus m v initial I hat. So the point is, you don't just subtract the two speeds, right? They're opposite directions. You actually add the speeds to get the change in speed, because we're subtracting what is actually in the opposite direction, negative m times that speed v. So it ends up becoming the sum of the two. So that's just a little thing. Intuitively, you get it. Sometimes when you're doing problems, you kind of forget that it's actually a big change. And then in the end, this change, the direction of that change vector is up, right? Final up minus initial down. The total vector is up. The impulse is up, which makes sense because the force is up. The table pushes up on the ball. Right. When a car drives along the road, it moves forward because the tires push against the road, and due to the friction force, the road pushes back. So a car can move because of friction. Even when you walk, you're pushing against the sidewalk, you're pulling back against the sidewalk, but you move forward really due to the friction force pushing you back. And sometimes when I walk, I like to try to imagine it. I'm not pushing against the road, the sidewalk is pulling me. Just see if you can imagine the sidewalk pulling you. It will lead to some strange contemplative walking. Rocket engines. So now, say we want to go into space. They can't really do this. Okay? There's no friction. There's nothing to push against in space. So if we want to move in space, what you got to do is use the conservation of momentum. All right, so let's think about a rocket. So, you know, it's giant sort of structure, and it's got kind of a nose on it. It's got some fins to make it fly straight. But the important thing is on the inside. Inside of here is the fuel, or the propellant. And when the fuel's inside the rocket, before you light the fuel, before you do anything, the whole thing is a system, and its momentum is 0. Because it's sitting on the launch pad, or in this case, let's imagine it's just in space and not moving. Well, what you do, you light the fuel, big chemical explosion happens, and the fuel shoots out the back. Oh, here's the fuel. And it's moving very fast. At V fuel, and therefore the rocket ends up going this way with its fins and everything, and it's going at some speed, V rocket, due to conservation of momentum. The final momentum of the system, in this case, is 0. For two reasons. One, momentum has to be conserved. And two, if you look at how it could be 0, remember, it's a vector quantity. They both pick up a speed, they both pick up a momentum, but since momentum's a vector, they can still cancel. So if you read about the analysis of rocket thrust and motion and the speed of the exhaust that you need, all these things, it gets very complicated, because here's what's really happening in a rocket. The rocket needs a lot of fuel, right? You want as much fuel as you can get. This whole thing is fuel. And as it starts to burn, you send some of the fuel out. But as it burns, as it comes out, a lot of the fuel is solid and it's still in the rocket. So in the early stages of the burn, a lot of the mass of the fuel is part of the rocket that was accelerated or that was pushed or given momentum this way, and then as it burns, then it comes out. So that makes it more complicated. Basically, the issue is that you have a change in mass per unit time. You have a dm dt, as we would say in calculus. And that just leads to more complicated analysis and something we aren't going to do. But in the end, what you need to make a fast rocket is a large mass of fuel and you need it to come out really fast. So the result is not too surprising. It's just getting there is pretty complicated because of this issue of the significant mass of the fuel. But I have another rocket over here where that won't be an issue. So this is an empty water jug, and it's got a little bit of fuel inside. And I'm not going to tell you what the fuel is because I do not want you to try this at home. But trust me, the mass of the fuel inside the jug is very small compared to the mass of the jug. The jug is suspended from the high ceiling on thin strings, and it's like a very long pendulum, so it's sort of an approximation of free one-dimensional motion. So I'm going to light the fuel, but first I'm going to turn the lights out so you can see a little better. And here we go. Let's see. And that was a good one. Well, that was a little more exciting than I intended. Let's see, so let's just analyze our rocket a little bit. It was a water bottle, and it had a nozzle where normally water comes out. And let's see, I can tell you a few things about it. The mass of the rocket is about 0.69 kilograms. That's just the mass of the water bottle. At first, the momentum was 0, right? But then after we lit it, the rocket goes this way with some velocity Vr, and the fuel goes this way with some velocity Vf. We can calculate the change in momentum. We can calculate basically the impulse that these applied to each other. I analyzed the video and measured Vf, the V rocket, to be about 7.2 meters per second. Okay? So we can get the final momentum of the rocket. It's just mass times velocity. It's 0.69 kilograms times 7.2 meters per second, which is about 5 kilogram meters per second. So if we want to think in terms of impulse, even though it's internal, we can think of the impulse each applied to the other and still conserve momentum, then the impulse is also 5 kilogram meters per second, because the impulse is equal to the change in momentum. This really is the change from 0 to 5. Since we have the impulse, we could say I equals 5 kilogram meters per second, which equals the average force times delta t. So also from the video, I was able to get approximately what delta t was just by watching the frames, and it was about 5. We're going to divide 5 kilogram meters per second by the delta t was about 0.375 while the rocket or the fuel was coming out and really pushing. So from that, we can get the average force of the thrust on the rocket. It was about 13 newtons. So not huge, but enough to really get it going. And this is all ignoring air resistance and the little strings pulling back and everything. But as an approximate situation, when you have the case that your fuel is very light and doesn't really contribute to the mass, this is how you can just solve a simple problem.